Good morning, mga Bisaya. So in this video, we will be discussing this particular steel frame. So this is a question from a fourth year civil engineering student. And so this is his question. So this is basically like asking what to consider in his design, considering that this building is close to the fourth line. And he was asking like what can I suggest when it comes to design. And so I asked him further about like what are the dimensions, and then his concern basically was um with his analysis he ended up this section. He said edge column is W27 by 84 and the intermediate columns were W18 by 106. So I'm not even sure why the edge columns are bigger or deeper than the intermediate columns. And then he said it still fail in deflection. So he meant by story drift. Now I asked him like I am not no longer familiar with how seismic analysis is done in the Philippines because I told him like I've never had a local project, and the last time I even calculate a seismic like analysis was when I was still at the university, and that was like 2000, 1999, 2000 maybe, probably 2000. So, and then if I remember correctly, in the calculation, you only have to select between zone 2 and 4. And then if you are closer to zone 4, then you have to use a certain coefficient. But what I'm used to is the because this procedure is still based on UBC 97, and I have different, or I am experiencing another like standard, or I would say. So basically, this is the warehouse. He said this is a warehouse, so this is basically their um, final project. I assume like final project for graduation. So he said, this one is um, this one is, oh, this one is W 27 by 84, and then the intermediate columns W18. And now, by looking at the sections, you would notice like why would you have a shallower beam um, in your intermediate column, intermediate frames, when that's where the biggest stress when it comes to a structure like this one, because this one here you have more in columns versus here. If this is clear span, then that's heavily loaded considering the tributary width of the frame. Now, and I told him like if you want, because like this one basically in this discussion we will discuss, or in this video we will discuss like what to consider, and then how to do like a more efficient um, structure. So I told him like the only time I've seen a wide flange like a regular W section used in a structure like this one was in 2012 in this one here. Because I told him like the most efficient section would be the taper section, the non-prismatic section. And then I told him like the last time I would say the first and last time I've seen a pre-engineered building that uses a W section is this one, and this was in 2012. this is a shock, and then I would understand that um, why this is a double section, because maybe the um, or not really understand, but they have an idea why, because they have this intermediate support, and then the bending in this frame is not so big, so maybe that's why a regular double section was chosen. But I am not sure also, because if this is using MBS, the metal building software, the software will select itself. Because I used to be an engineer of record for a metal building manufacturer. Um, I just can't discuss it openly, because it's not an NDA, but they are protecting their system, because it's a first. I mean, it's utilizing the same like frame, but they made some tweaks in it, and it's a first. And I just can discuss openly about it. And we even have a project before. Um, well, we stopped working with them already anymore. Um, but the last time we heard from them was they were asking if um, I am able to help them like for a project um, in the US, and it has something to do with outer space. So you already have a clue what it is or what it's for. So, but we declined because first we don't have a permit to practice in. I mean, I have license in the US, and it's easy to get license in that state, but we don't have permit to practice there. We don't have company like insurance, those kind of stuff. So we declined. And then, so anyway, so back then we are using a software from like it's called MBS, Metal Building Software, and all you have to do is basically just you know, input the location, the geometry of the building, and that's it. And then everything like even connections, details, like details of the connections, it will automatically output like all of those information, and then the software will select the most efficient section. Like it will even like detail like a splice, like um for example I have here a W, or so for example this one, like it will even calculate for example it will divide the web of this column in three, and then this one will be really thin, like say this is one say 1/8, and then this is say 1/4, and then this is 3/8, something like that one. It will automatically calculate like assign sections, which basically gives you the most efficient um or basically most efficient section. And then after that, it will even calculate the entire, because the fee for this, like for to stamp a structure like this one, is based on the weight of the building. So the bigger the heavier the building is, then you'll be paid more. So and and my supervisor didn't like that that I would say it's not an agreement, but that I don't know how you call it. Um, that kind of like a system of like like we stamp, and then like, they pay us with whatever, like based on the weight of the building. So I think we managed to stamp, I think like at least five maybe or six projects for them, and then we stopped stamping their drone. But anyway, so this one, because I told him like the most efficient section would be a non-prismatic section, or the tapered section, like like this one here. So if you notice, you have, tapered. Usually, I've seen pre-engineered building with only like 12 inches here, and then right here at the hands, it's like 38. I've seen because I did a lot of foundation design for this kind of structure, but most of the time I will do a map calculation because by the time I'm designing the foundation, we still don't have the still drawings, and I need a reaction to design the files like the foundations. So what I usually do is I will do a mock-up calculation and then apply all the load. And then because this one it's complicated to model, so what I will usually do is I will just assume a W section like standard section, and then what it does is it will just give me um the reaction will still be the same when it comes to like snow load, wind load. It doesn't matter, it's still the same. But for the dead load, because I'm using W section so that it's just easy. Basically, all you have to do is just select a certain section and then assign it to the frame, and that's it. You don't have to model a non-prismatic section, which is more complicated to do that. So um, when I if I use a W section, then it will just give me a heavier reaction, which is more conservative and which is fine. I mean, design wise, with regards to foundation, and then so I do like the foundation design, detailing everything, and then once we get the still drawing, I will now compare the reaction from the steel manufacturer versus the reaction I got from my calculation, and then most of the time my calculation is conservative, but there are times that the the reaction is sometimes like 5%, or the reaction from the steel manufacturer is like 5% higher than what I calculated. So um, after that, like my practice would be once I model this frame, I will just add another 10%, and then I will design the foundation based on that one. Like the reaction I get from my analysis plus 10%. And since then, it's always higher than the reaction from the steel manufacturer. So um, I don't have to change my calculation again. But anyway, um, so this is his frame, and then we're just discussing uh, like for example, like what are these, like this one here, like this blue one, uh, like this one. I mean, I understand these are strut, but I'm not sure how big the loads are, but most of the time, pre-engineered building will use will avoid this one, and then we'll just use because um you still have girts, right? You still have girts right here that will support your cladding, like on the walls and on the roof. You still have girts like this one here, this one, right? You still have girts, and then you have portlands. You have portlands on the roof supporting the roof cladding. Now this one, in this particular frame, the strut is basically used to transfer the load from one side all the way down to the entire um, length of the depth of the building, and then transfer that load to your cross bracing. Now, um, I think the most important here is for seismic analysis. For seismic analysis, your weight or your base shear is a percentage of your weight of the building. So the heavier the building, the biggest the base shear, no? For seismic calculation. That's why um, it is better to make your steel structure like efficient when it comes to the weight, like using all these members here because it adds up, like all um these members here will add to the weight of your structure, and then eventually the magnitude of your base shear. So I did a sample calculation because I don't have some information back home. So what I did was, so this is a sample calculation for a, so this the location I use is Victoria in British Columbia. If you noticed, if you look at the map, so this is Victoria, and then this is really close to the San Andreas Fault of California, right here. Then there's another fault here. I just can't remember the name, but San Andreas is right here. San Andreas Fault in California, and um, yeah, the base shear that I got from this calculation is 0.966 kilonewton. So because I assigned a weight of like just one kilonewton, 1 unit here. So whatever is the, so this is basically 96.6% of whatever the weight. So imagine, um, I don't know in like back home, like what would be the percentage for the base year, but using the National Building Code of Canada, like provision for seismic in British Columbia, like Victoria, the base year is 0.966 of the weight, or 96. So what if your weight of the building is 100, then your base year is 96. So that's really big, right? So that's why you have to make sure that your sections are efficient. Now, when it comes to transferring the load from, because you have to transfer like all the wind pressure from this side, right? So wind pressure from that side, it will be transferred to this lateral bracing. So that's given. Now, when it comes to um, number of like braced bay, so this one, base with bracing, you also have to I would say optimize the capacity. Like usually the tension rod that's used for cross bracing in metal buildings that I've worked with, like designed the foundation, and even the cross bracing, or the, yeah, tension bracing, tension rod for the steel building that I used to stamp, ranges from like half inch, 5/8 to 1 inch diameter, and then it will optimize the capacity of that one. So sometimes in one building, you only need like one or two cross or braced base. So right here, if you can have like one in at each end. So well, like I said, it really depends on the load. So maybe in this particular calculation, it requires more bracing. And then when selecting a bracing, um, the most common bracing for metal building is tension rod. Using tension rod. Um, to be honest, I've never seen a metal building that uses angles, or HSS bracing. It's always tension rod, and then tension rod, or if there is no room for bracing, it will use a portal frame. I don't know if I have a sample here for a portal frame. Yeah, this is the cross bracing. Yeah, I don't think I mean, I have lots of projects with portal frames as the lateral force resisting system, but um, I thought I included in all the photos that I um, see or put here in the slides. But anyway, so basically, what a portal frame is, so for example, if this is your if this is your building, and then you know you have lots of overhead doors, because usually structures that uses fringe and building are like warehouses and shops, and you have tons of overhead doors. Now, since there is no room for, because this is usually like just sometimes 3 feet, sometimes 2 feet. So since there is no room for cross bracing, because you won't be having cross bracing here because that's an overhead door. So what um, the software will do is it will assign a, so if this is the framing here, so between the framing, it will have like a frame like that, and then you will have like a strut there. So this will be the one resisting instead of the usual cross bracing, because this is an overhead door. Then it will use a portal frame. And so on this one, I asked him like, where are the locations of the entrances? He said it's only um, at the front, like here. So in this case, for sure, cross bracing would be more efficient because it's cheaper compared to having a portal frame. So that's one thing, like if you can minimize the number of cross bracing, just optimize the capacity of the tension rod, whatever bracing you are using. Just optimize that one. Maybe you can eliminate some of this cross bracing. Now, another consideration is, well, like for example, like this one here, he has a cross bracing here on the roof, but nothing in here, which is fine because all you have to do is once it reaches the force reaches this side, you can just transfer that um, to the bracing using a strut like this one here, the blue ones. But the most efficient section or most efficient framing would be if this is your braced bay for the roof, then that should also be your braced bay for the let's clear this one here. So if you notice here, uh, so he has a bracing. This one, this is the a braced bay on the roof, but nothing in here. So like I said, once the load reaches this frame, it can transfer to the frame to the cross bracing next bay, which is fine because this will be designed as a strut. But like I said, the most efficient would be if this is a braced bay for the roof, then make this as a braced bay for the walls because this way you can minimize the requirement of these big struts here to transfer the load to this next braced bay. So that's another thing. And then another consideration would be instead of using a strut, um, I would say on all the buildings, like metal buildings that I designed the foundation for, um, I would say like 99% they don't have a like a separate strut. They will use the girts and the purlins to transfer the load. So this one here, for example, so on this particular building, the all the lateral forces are transferred through the purlins and the girts on the side, like this one, because this one here can still resist like compression, because that's basically the purpose of the strut, to transfer the load from one section to the other, and then all of it will be transferred to the wherever is the cross or the cross bracings. So um most, like I said, 90, I would say 99%, it will utilize the girts and the purlins for transferring the compression to the cross bracing, and then this example here, this is one of the buildings that there is actually a separate strat, and you will notice it. This one here, this one out of web rafter. This one here, and then there is this HSS. There is this circle. There is this circle. I don't know why this is pipe. This is HSS, but if you look at the plan, see, if you look at the plan, it has a strut, this one. So basically, one of the reasons why there has a, like this particular frame has a separate strut because the load is larger than the other because this is designated or designed as a post-disaster building. And then for seismic, you increase the importance factor that will basically increase also your lateral load from a normal building. So that's why the react or the lateral. I mean, you can design a bigger or stiffer purlins because or to transfer that load, but maybe in this particular application, the software um, realized that it's better to assign a strat rather than relying on the purlins. But if it's possible, just use the purlins because that if you remember, so so for example, of course, like you have, so this is your frame, right? This is your frame, or let's just say, so like that one. So this is the frame from another bay, and then your purlins is right here, right? Something like that one. That's your purlins. Now all the loads basically is transferred to this. So the loads is coming from the walls, right? Coming from the walls right there. And it will be transferred to the frame right here. Now, if you notice at this joint, you will have the frame, and then you have the four links like that. So the load is from this frame to the four links, and then transfer that to the other frames, and then back to the cross bracing on the roof or down to the cross bracing on your wall. Now, if you if you look at this closely, so your force is basically it starts from the joint here, like I mean, transfer from the wall to the frame, and then it transfer here. So this force at the joint, this intersection here, that force will create a compression at the same time negative bending of the purlins. So the purlins will bend upward, right? It's the same as if you have like a pre-stress, um, you know, pre-stress girder, and then if you position the tendons at the bottom, this will bend upward, right? And then it will be countered by the weight. That's why it's ideal to have the tendons um, below the neutral axis so that it will create a bending upward and then to counter the gravity load. So it's the same as this one. So if you have load right here at the base of the or at the underside of the purlins, this will result in bending of the purlins upward. And then you have of course the gravity loads. You have the the snow load, you have the dead load, and then whatever if you have, roof live load or any rooftop unit, or if you have collateral loads. So that's downward. So at the end, it will counter each other. So it's more efficient even to purlins with regards to resisting the gravity loads because the lateral load will bend the purlins upward, and then it will be countered by the gravity load. So that's even better in that scenario. That's why the purlins are used to transfer all the lateral loads to your bracing. And besides, these purlins are spaced like what, 4 feet, 5 feet spacing. So it's more of like a uniform load, uniform support. So for example, on this one, what's the spacing here? Uh, so see, the spacing here is only like 3 foot 6 spacing of the purlin. So that's really close. So that's um, even better in transferring the load, and yet they still have a strut. So it really depends on, like, if you rely like, basically what happened here is, in transferring the load from the middle to the outside walls, or to the braced bay here, it relies on the purlins to transfer that load. But once it reaches right here, and of course the reaction is bigger than in the middle, because this is more of like it's the same as if you have, you know, if you have a uniform load beam. So your shear at this location will be smaller than at the support, because this is where the maximum reaction. So it's the same here. So maybe in this situation, the purlins here, or it's called Eve strut, is not enough to transfer the load. Then much better to have a separate strut. But the project, the manufacturer, like the steel manufacturer that we work with, we don't have this luxury, because, like I said, we are using different system. So at every intersection, like in this case, for example, if this is my roof framing plan, so every braced bay, I will have a strut right there. Mm. Because I need that to transfer the load, because we don't have four lanes. Um, so like I said, it really depends. So um, since I would assume that he is doing this using different software, unlike MBS, where like I said, with MBS, all you have to do is just input the location, and then the converting code, and then the geometry of the building, and that's it. Just when you hit enter, like I said, you can finish. You can finish the model like in like what, 30 minutes, and then you will have everything, like all the details, because it will also have like the detail itself is included in, like when you hit enter, like, to run the analysis, the result will also include all the details, like connections of all your components. So that's what MBS does. So unlike any other software, for example, when I do a mock calculation for getting the foundation reactions, I'm using SAP 2000. So in that case, I have to really model everything, and then just make assumptions that, for example, I don't have to model the purlins to transfer the load, because all I have to do is just apply the load, apply the load as a joint. Because at the end of the day, like, for example, all the loads in this wall, half of that will be transferred to this frame, and then half of that will be transferred to this frame. So I will just analyze this one, apply the load as uniform uniform load. But in metal building software, you don't have to do that, because he will calculate, like, the software will calculate itself, like everything. Like I said, all you have to do is input the geometry, the building code, the location, that's it. But if you're doing it manually, so you have to apply, frame by frame, like uniform load. So in that case, I have an option, like how to, apply all my loads. But if you do the proper design, if you're the one designing the superstructure, then you have to consider all of this. Like, do I need this extra diagonal bracing here? Because you have to understand what's that for. Like I said, for example, this frame here, this blue one. I know that is transferring the load like a strat, but like I said, you have to consider that there is also a four lanes that run along this direction, and it can potentially carry all those compression forces. It's not that big. I mean, what's your wind load here? Would be like what, 5 psf or 10 psf. So it's not that big. And I mean, if it's done like for other buildings, I mean, why not? Why can't you? So it's a matter of I mean, in this particular project, since it's just a I would say a capstone, like a project for compliance for graduation, then it doesn't really matter how you, how you frame it. I mean, at the end of the day, I mean, even if this is an actual design, it's your design. So whatever your preference is, then that's fine. But what I'm just saying is, you have to always remember that this one, like I said, your base year is a percentage of your weight. So like I said, this is in Victoria, BC. It's close to the San Andreas Fault. That's 96.6% of your building weight. That's your base year. So if you can minimize the weight of your structure, then much better. Because the heavier your structure is, the bigger the lateral load. Then it will now this one it will become more bigger. So you know if you are doing it manually, then imagine how many iterations you have to do. So good thing we have software. So that's one thing to consider. So first, location of the bracing. If two braced base is enough or not, then um what else? Let me check my list here. I have a list of um things to discuss here. So yeah, I guess we already talked about the bracing, the framing. Um, like I said, so first is the shape of this building, or the geometry of your frame. It could be the most efficient would be non-prismatic. And then I also told him, like, when he asked for um because he is worried that these sections are already big enough. And I told him, like I said, I do a mock-up calculation for my buildings, right? And then it's only like most of I think the tallest region building that I did was only like 28 feet, I think 28 feet. And then when I do my calculation, like I said, I use regular section, and most of the time I will have like W24, sometimes W27, W28, something like that. So it's not, and I think there was one because the span was 120 feet, I think. And the section I got was W36 by 100 something. It's really heavy. So looking at the section that he was worried about, like 18 W27, like that's nothing considering that the weight of the building is, or the height of the building is 14.5 meters. So what's 14.5 in feet? So that's like 47 and a half. That's really that's really high, for a single story like a steel frame. So imagine the what would be the section. So I would expect that the section should be maybe at least W24 or W36 maybe. So he's worried about this one, and I told him, like, no, that's considering the height of the building, that's nothing. And so basically, he said, okay. I thought he thought that this section is already like really big, which I understand because he's still a student. So I told him, yeah, that's nothing. So just proceed with your calculation, and then don't worry about that one. That's a really small section compared to what I got when I do a mock calculation. So even this one, like this building here, I think in my calculation I got W 27 or something by 100. And this is only like 20, what is this? Like 22, 23 feet, 22 feet. So that's only 22 feet. Like that's basically half of what he has, you know? So I told him like, that's nothing. Just proceed with your calculation and select bigger sections. And then maybe uh, by the time you practice, um, your profession, or when you become an engineer, and then when you design something like this one, then maybe it's time to consider the non-prismatic section, like the tapered section, because it's really efficient. It's efficient, and it will make your structure lighter, and eventually your lateral load will be smaller. Then another thing to consider is the effect of this bracing. This one. So this bracing here actually helps um with your main frame, because so this one will be negative bending. So your moment will be like that one, and then this one, and then it will go like this, like that one. So in within this area, that is like bracing is not that. I mean, you still need bracing at that area, but not the same as in this region here, because the bracing is helpful for your compression member. So, for example, in this area you have capacity bending, so your compression will be the top flange, but you have four lanes already. So that braces the your frame against torsional buckling, because if it's the unsupported length exceeds the limit, then it will reduce significantly your capacity, because once it considers the buckling, the lateral torsional buckling, then it will significantly reduce your capacity. So in this region where your compression is at the bottom, that's why this is really important, like bracing right here. The same as right here in the what we call this one. Um, the same in with your column. So you have bracing. See this one here. So this is also bracing from your purlins. Let me see if I can find a picture with those. So I don't know if you can clearly see this one. So if you notice, so we have this bracing, right? Uh, So you have this bracing. Yeah, let me just find. So you have this bracing your so you may think that it is the purlins being braced on this one. No, it is the purlins bracing the frame. So that's um the other way around. So it's the purlins that brace the what we call this one, the frame. And then in this case, I think this is not done yet, because you can see the plate here. This is the plate there. So that is for the bracing in this direction. So this one. So it's not done, because this is an ongoing construction. So the bracing were not placed yet. This one. So you will notice that on here, like a um share plate. So that's the purpose of that bracing, to limit the unsupported length of your frame, and then eventually reduces your required section. Now, so we already discussed about the stress, the bracing, and then we will discuss the because I told he said like he was also asking like the foundation for equipments, and then where is the I told him like are those equipments like static or like it has like it will vibrate, you know, like dynamic loading. So he said like most of it are static, and then some are, you know, moving equipments like because this is a factory. He said. So I told him like if it's just like a static equipment, like you know, just the gravity or supporting gravity alone, then all you have to do is what you can do is have some kind of it's either separate footing or you can have a monolithic footing with this slab and then just make it thicker, you know, based on the requirements like, you know, bending, punching. But if it is a dynamic, there's a dynamic involved, like a moving equipment, like rotary or whatever, you know, so for example, generator, it will vibrate. Then the best option, or what we usually do is, we will have, if this is a slab, we will have a separate foundation for the equipment, and then we will just provide some kind of like a gap here, normally half inch, and then we will provide uh like a sealant. uh, so we'll just seal this part here, and then expansion joint material like a it's like a rubber, like a asphalt impregnated membrane, and then with sealant on top. So usually we have half inch gap, so that if this one vibrates and then this will move, you know, a little, then it will not create, you know, it will not create a um, force transfer to your slab and eventually lead to cracking of your slab. So you have to have a gap here. And then the reason why this is big is because you need a heavier foundation to dampen the vibration. So imagine if you have an equipment sitting on a say 4 inch slab versus a 30 inches slab. So the 4 inch slab will vibrate more compared to a heavier foundation. And then another thing is most equipment have some kind of like a base isolator that will also help. So why it became a star. Anyway, so it has um isolator here, like seismic isolator or like base isolator, whatever it's called. Then it will help with regards to vibration. So and then I told him like when it comes to this one here, you know, what exactly is the purpose of that one? And then is that grade beam supported by the ground or is that suspended? When I say suspended, I already discussed about this before. Like in cold climate, your grade beam is always suspended, and then when you form that one, you only put like a void form here. And usually this is like 4 to 6 inches, and then that void form is designed to collapse over time, leaving a gap here. And then by the time the soil underneath like heaves, then it will not push your grade beam up. So this is like a caution. So this is always suspended. Like when we design grade beam here, it's always suspended because of that void form here. So I asked him like, is that supported directly by the ground? I said yes. But regardless, even if it's supported by the ground or it is suspended, this is most of the time like overlooked. Like some engineers do not consider this one. I've noticed that in many of the because when we do like an addition, when we do additions or renovations, and then of course you have to look at the existing foundation, what it looks like, you know, and then when I calculate the load, and I most of the time I will notice that the axle load, uh, the weight of the vehicle coming in and out of the building is not considered. Now imagine, I mean, if it's just like a, you know, people coming in and out, that's fine. But if you are talking about, if you are talking about like Caterpillar, like dozer, those bulldozer with like those trucks coming in and out of this building, and then you don't consider that one. Imagine how heavy those um, dozer or even the those trailer, semi-trailer, like tankers. So imagine, say for example, so imagine if you have, you know, if you have trucks coming in and out of your shop or building like this one, that's really heavy, like this. Or if you have Caterpillar dozer, this one. Imagine if you're a mechanic shop and then you have equipment like this one coming in and out of your shop, you know. So this is really heavy. So that's why on this particular one, I asked him like, what are the kinds of vehicles that are expected to come in and out? Like I said, okay, just forklifts. So okay, just design this with forklifts, but what about the trucks that are bringing the equipments in, right? So like I said, you have to consider all those things. So what I usually do is before I start the design, I will ask the owner like, what are the expected uh, like heaviest trucks that are coming in and out. Then he would give me a list of, all kinds of trucks that are possibly like if this is a shop, then I will ask like, what kind of are you like a heavy mechanic shop? Then I would expect that there will be some kind of, dump trucks and dozer and, you know, tankers that would come and out um, from the building. So if that's the case, so when you design this one, you have to account for the um, vehicle load in your grade beams and foundation as well. So um, what I usually do is, if, for example, this is the grade beam, and then typical is this is like brace bay for or typical base spacing for metal frames is between 20 to 25, and then this is continuous grade beam, this is continuous grade beam. So, and then this is your overhead door, the weight of the overhead door, like that one. So say this is like 16 feet, overhead door, 16 foot wide. So this one is 16. Now, typical wheelbase of a vehicle is between 6.5 to 7. I've seen common is 6.5. Sometimes I've seen 7 feet wheelbase, but for the sake of discussion, let's just say 7 feet. So now you will have an axle load that is, coming in and out of the building. Then all you have to do is determine whatever is the estimated axle weight of a truck. Like for example, if it's a dump truck, then the heaviest, you know, the lead axle would be smaller because this is where the driver is. This is usually lighter compared to the weight, carried by this one, even just the bare weight. So when I design incising the grade beam, I will use the axle load of the rear axle because that's where the heavy loads are. And then um, in the framing plan or foundation plan, I will clearly indicate that the maximum axle load is say 24,000 pounds. And then if that's the axle load, that means half of it will be 12,000 pounds, 12 kips, and then this is also 12 kips. And then this one, because this is moving load. I mean, I can't imagine doing this like manually, but I use SAP in sizing, like analyzing this one. So what I will do is I will assign a moving load from this joint up to here, you know, and then the spacing is whatever is the, say 7 feet is the space wheelbase. So I will apply that moving load, moving load from here. And then if you have an adjacent overhead door as well here, then you have to consider that that one is, acting simultaneously. Now, if the reaction is really ridiculous and it's really big, what I will do is I will, for example, this is my frame here, and this is overhead door one, overhead door two, overhead door three, and then I will not apply these loads all together. Sometimes I will use one and three, that one, and then I will make a note that no vehicles enter the building at the same time, for like adjacent overhead doors. So you have to clearly specify that one, that it is not allowed. Otherwise, you have to um, you know um, assume that the worst case would be, one and two, and then one, two, and three are, at the same time. These three vehicles enter your building at the same time, which is highly unlikely. But at least it is clear in the drawing what are your assumptions are. But I always consider the actual load. So this is most engineer overlook, like this one, that they don't consider the actual load, but you have to, because of course, if this grid beam is just designed for walls, and then or whatever you load, because okay, there's a wall here, and there's a wall just over the door, and then you only consider the weight of this wall for loading this one. No, because like I said, you have a vehicle, and this is way 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 heavier than your walls, you know so sometimes this dictates the final sizing of your grade beam, and then at the same time your foundations, your piles. So these are the things that you have to consider when designing a telestructure. And then one thing also I've learned from other engineers, because at one time we were hired, like it was during COVID time, and the engineers from like a sawmill, the engineers are from other province, and then during COVID the travel restrictions are really strict, and then it's really difficult for them to do the inspection. So we were hired to do the inspection in their behalf, and I have to go to the plant, I would say, at least twice a week, and that is for 2 years, 3 years. And it's a big grade to the sawmill. And then I noticed, like, because sometimes, like, when I do the inspection for them, even if I'm not the one designing it, I still have to you know see, and then try to understand, like, how everything is how everything is designed, and then what are the things that being considered. And then when I look at the frame, like, why is this so big? And then I've never seen, like, the structures are so big compared to the demand. I would say, like, the load is just really small, and then the supporting beam is really big. And then at one point, I was really curious. I asked the engineer, like, I know, just it was just like we were discussing like an items that I found. Um, um, it's more of a. It was not. It's supposed to be installed first before doing that pen, but it was the the activity was done, or I would say it was basically the frame will be installed um after after. So it should be installed before, but it was installed or it will be installed like after, because when I did the inspection, it wasn't there yet. So I confirmed with the engineer, and then he said that is fine because all of this structure in a way are, are overkill. And basically he said, um, how to frame this one. Basically, he said like, when they design this kind of structures, they will always assume that there will be upgrades in the future. There will be changing in loadings and whatnot. So they will size the frame usually double the required capacity in that particular, at that particular time. For example, the structure is supposed to be like, just an assembly without, without regular loading, without the equipment. They will use it for say 100 PSF, but in their practice they will design it for 200. So they will always, or not always, but it depends on the type of structure. So in that particular plant, they already oversize everything, in anticipation that in the future um, there will be modification or change in the loadings, because I personally experienced that one, because I used to work with this um, sawmill as well, with all this, with all their upgrades, and then I will end up reinforcing beams, reinforcing column, just to meet the new demand. So based on that one, with that upgrade, I realized like, yeah, that's practical way of designing a warehouse, because it's true, like you will never know what would be the future occupancy of that building. So to avoid any, imagine that's a, like, doing like when I do like upgrades, I have to, even doing inspection in that sawmill, I have to make sure that it coincides with the day they are, doing maintenance and they are shut down, so that I won't affect their operation. So imagine if they keep on upgrading, and then they will, I mean, basically, when you analyze it, you will keep on, you have to reinforce columns and foundations, and imagine the effect on the operations if you try to, I mean, how can you finish a, say, for example, if you reinforce a foundation, you have to excavate, you have to, um, pour the concrete, and then you have to wait until the concrete is cured. So that's, I don't know what, how many days, even if you use the early strength, like 7 days, early strength concrete, then you still have 7 days lost in operations, right? So that's why in new designs for some structures like this one, the engineers would um, already consider like higher loads just in case. So I don't know other engineers what they will do, but based on my experience, this is what I've observed, what I've noticed from other engineers as well. So one last thing to consider on this one is um, the foundation. Now, I would assume, because pile foundations for buildings back home is not really common. So I would assume this will be footing, right? So assuming this is footing, so this is your steel frame, and then this is your this is your pilaster or pedestal, whatever you call it, and then this is your footing, right? Now, from a metal, if you have a building like this one, it's like, I've never seen a moment connection right here. It's usually, or typically, a pin connection. But regardless if that's pin connection, this vertical load will always result in a kick. You know, it will push the column outwards, and then in addition to that, you have wind load. So this one in addition to the wind load. So that would create a huge lateral load to your top of pilaster or to the base of your column and then eventually to the top of pilaster. And that will be what? That will become a shear in your footing, sliding force. At the same time, you have a large moment, which is equal to P times E. This is your P, this is your E, right? Now, well, you can neglect all the passive resistance here from your footing and then from your baluster, from the soil, and then you design this to resist, you know, to resist the sliding and then the overturning. So when you say sliding, well, you have heavy structure anyway. So you have your frictional force there. Then your frictional force, if is equal to the mu times n, this is coefficient of friction. And then coefficient of friction between concrete and soil. Ah, ito na naroon. So, we're preparing binignit. So, we're, so this is frictional force, and then this is mu times n. So say point, probably like coefficient of friction between concrete and clay is point 0.3, say point 0.3. Um, that is the coefficient of friction. Then the n is the weight. So that weight includes the self weight of the structure. Do not include live load. No, do not include live load, snow load, wind load. These are transient loads. Do not include that when you calculate for the normal way to calculate for the frictional force, because what if live load is not present at the time? What if snow load is not present at the time? So always consider just I mean, you can consider any other loads if you want, but in my practice, I always just consider the self weight of the structure to calculate for this frictional resistance. So that's why there was there was a like an argument in my earlier post when I had a foundation based on I only had the like a taken foundation like at grade level, and then one engineer commented like that fails, and I don't know. I will not I just think and he doesn't know what he's talking about. So he's not just exposed to this kind of you know. Anyway, so it's common. Like we have hundreds of slab and grade. Like I said, even the hotels I did in the US, those are 3-story, 4-story buildings, and then the foundation is just at grade level. Taking slab, rough foundation. And I would say I've personally designed more than like 250 hotels in the US, and I would say 90% of it were just slab and grade taking edge. So maybe in the Philippines it's not common, but it's common in North America. So, and the thing is like, oh, it fails and it violates the NECP. Well, that's according to you. Anyway, so this is one of consideration. Like you have to consider for the frictional resistance. So you don't, you know, um, because you still have to satisfy the sliding and overturning. So overturning. Now, if this is overturning, all you have to do is just make so you have your normal weight of the structure, right? And then you have your, say, if this is, concentric, then your weight also of your footing is right there. That's why in most cases, if you are doing a foundation like this one, this will be really thick so that it can withstand the overturning. Now, the other way, since you have grade beam anyway, this one, why not consider the passive resistance of that grade beam? So, for example, this is your footing, or this is your pilaster, right? This is your pilaster, and then this is your footing, like that one. Now, you already have grade beam here. Say this one, this is your grade beam. I would assume that the pilaster is wider than the grade beam. So, say, for example, that's the grade beam. Now you can consider this as, to resist the lateral load. You have your frame here, then you have your lateral force. So you have your, what we call this one, like passive resistance of your grade beam. So that's why I have a project where I utilize this kind of foundation for a Prince building. I have this perimeter, and then I design this to resist the lateral load, because there is no pavement here. It's just gravel, because it's just like a cold storage, storing all those timber. Um, like it's a lumber yard. So this is just gravel. So there's nothing that support, um uh like you cannot utilize it. And like for example, I posted this in previous post in my page, where I have a, um well, I basically showed a picture of um a tie beam. So basically, if this is the building, then this is the column, right? And then what they did, is my first time seeing this, to be honest. What they did is they have a tie beam here. So the picture is in my page. I posted it a while ago. So they used a tie beam, and it's, I think, the rebar is 420 I think, and then this is 16 by 16, I think, if I remember correctly. But in my practice, like what I usually do is I will just utilize a hairpin. It will be wrapped around the, so for example, so this is your column, right? And then this is your base plate. Then you have your, what do you call this one, anchor rod. Then this one here will be wrapped around, right here, wrap around the tension, the anchor rod, so that it will resist the, so this is called hairpin. So it will resist the lateral load, because like I said, the gravity alone, this one, the gravity loads will tend to, result in kicking of your structure. So basically, if we have a hairpin tying this together, these two, like this one, so you have hairpin here as well, and then you utilize this slab to resist all the tension, right? Because yeah, and you have a slab, and then it is reinforced, so you have some tensile capacity there. So this will, so what I usually do is I will let the hairpin resist the kick, the kick of the frame from gravity loads. And then the grade beam, I will analyze the grade beam to resist the external lateral, like wind pressure, this one, because this one will be countering each other, right? So if you have, there will be tension here. So this will counter each other, so that's basically zero. And then the external wind pressure, like the lateral, then that's the force that I will consider in designing or analyzing this one as a, like, passive resistance from the grade beam. So this could be, maybe if you need 3 feet, maybe, or 2 feet. The usual grade beam size here is 8 by 24, 8 inches by 24 inches. So you can make this 3 feet so that you have bigger, passive resistance against wind. So you can do that. Now, if you are doing this, your overturning, your overturning here will be minimized. So you can have a shallow or a, you know, thinner footing. Now, your footing will now be sized based on punching and bending only, if that's the case. So there are many ways of how to deal with this one, as long as you consider everything. Now, like I said, if there is no perimeter grid beam, there is no slab, then all you have to do is, you have no other option but to rely on your footing, to resist everything, like, sliding, um, sliding, punching, bending, overturning, like that. So what else in my list here? I think that's it. I hope everything is covered now. So, um, one thing, this one, I also noticed, let's clear this on here. So, looking at this frame, I don't see any cross bracing on the end wall, so I would assume that this is also a moment frame. Because I asked him, like, why don't you have a cross bracing on your end walls? He said, three of these space are obviously doors. That one. So he thought that this cross bracing has to be symmetrical. What he meant is, since there is no room for cross bracing here because this is an overhead door, these three here openings, he can only put cross bracing in this area. It's not allowed because it's not symmetrical. Like I said, no. If only one bracing is required, then so be it. All you have to do is transfer that. As long as you have the proper load path, that's the most important. No, you you have to make sure that you understand where your loads are going. So if your force, for example, is going in this direction, then it will be transferred through this frame here, and then through this horizontal bracing, and then you have claddings here anyway, so you will have girts. So that's the one transferring all the loads. So it doesn't have to be, you know, symmetrical. Or if it, what I mean is, if you put cross bracing, it doesn't mean that you also required put cross bracing in that area. So you can have one bracing, only at end walls. I don't know if we can see here. Hmm, where's the sample? Oh, here. See, this one. I mean, it's in the middle, but it's only one. It doesn't have to be like, opposite side, opposite each other. You can only have just one cross bracing. What I notice on this one here is, say, assuming this is a movement frame, which is fine. I mean, um, it's not uncommon, especially, well, the I would say the common framing for inwards basically is, this is like just a regular beam, you know. Most of the time this is only like W10 by 22 so far. And then this is W, say, 8 by 31. And this is like just pin connected here. Pin connected. This is just a regular beam, like shear, simple beam, simple beam, simple beam, simple beam. Because you can always utilize this one as your support, you know. So it doesn't have to be moment frame as well. So the only time manufacturer use a moment frame for in walls in framing is if this is expandable expandable frame. If the owner already know that in the future he will have some kind of expansion in this one, then this frame will be analyzed as any other intermediate frame. It will be designed, and then this one, the connection here will just have a like a slotted holes. The angle connector, the connector rail will have a slotted hole so that it will free to move up and down, but not laterally. So that's the only time they will use a humid frame here. If that is expandable frame, like, in the future they will decide to extend that building. But for the sake of discussion, assuming this is, moving frame, and the same on the other side, that's movement frame on the other side. Now, if you notice, there is a floor here, that floor. So that floor will have a lateral load here as well, like for seismic, right? And yet you don't have any, how are you, or like I said, I really don't know how he analyzed this one, but this is one thing that you have to consider as well. So since you have a floor here, then you have it's technically a diaphragm. Then you have to consider a lateral load halfway, right? Half of that. And then you have to consider how you support this laterally. So it's either moment frame here, like for your this interior column, the yellow one, you will have some kind at least one base moment frame so that it can resist lateral load. And then on the other side, you could have a lateral bracing here, a cross bracing, or if you rely on the capacity of the bending of the column, that's fine as well. But as long as you consider that lateral load from the mezzanine floor, so that's one thing you should consider. So other than that, I think that's it. So um, to the student who ever asked this one, who asked me this, I mean, if you still have some questions, you can comment to this video, and then I hope it is clear now. And then to other students or to other engineers who have questions, just let me know because I don't know if I already covered all your possible questions, but I hope I did. So if there are things that I left out or I forgot to discuss, then just let me know, and I will gladly answer that or maybe make another video. So anyway, I think that's it for now. Magandang pamiyong binignit. Bye-bye. Oh, by the way, don't forget to join the group structural engineers, structural engineering for dummies. I won't, I won't, I mean, I don't even ask you to follow my page. I don't care if you follow or not. But I would really, really recommend if you can oh, structural engineering for dummies. I would really, really suggest if you join this group so that we can share and learn together. I mean, if you have questions, you can post your questions in there. If I know the answer, I will answer it. And if not, I hope other members can share their knowledge as well. So let's share and learn together in this group. You don't have to follow my page, but I would really um, um, ask you to join this one if to grow our group and then learn from others experience and whatnot. So that's all I ask. Just if you can join, and then if you have questions, and I really encourage everybody also that for if new engineers are have questions, if you know the answer, I would really encourage you to share and um, share your knowledge or share your ideas or your expertise. I would be glad, if m- m- more members will be active in answering questions from our fellow members. So yeah, if you can, join this group. Okay, I think that's it for now. Thank you.